Hi, everyone. This is our project Ember, a geospatial approach to wildfire risk modeling using machine learning and remote sensing data. My name is Hudson. I'm from Westview High School in San Diego, California.
And my name is Riya Gupta. I'm from Northwood High School located in Irvine, California. Introducing our problem. Wildfires are a problem that has occurred throughout the world, with more than 7.2 million acres alone being burned in the US annually. Connecting this back to air quality, smoke released from wildfires creates particulate matter that can cause an increase in the prevalence of respiratory diseases. And especially with the Canada wildfire, which is a rare event that put more than 50 million people under air quality alerts, really showed the world what it looks like to experience such a large wildfire event. However, these kind of wildfire events are a yearly occurrence for many Californians, and which is why we really wanted to solve this problem. But currently, what does wildfire management look like? Many wildfire institutions predict wildfire using vegetation indices, weather forecasting, and other biogeophysical factors. However, these factors are currently not enough, as more than 90% of wildfires are started by human activity. As such, it is important to understand the impact of human use of land cover and other factors as well. Wildfire presence. Here's a picture that I took of a wildfire, and you can kind of see how it correlates with PM 2.5 values in that area for that year. This is from the Silverado wildfire. So introducing their solution, we wanted to create a machine learning model that could provide real-time wildfire risk maps of the US. Our model currently covers San Bernardino County, California. We chose this area because it includes both a high risk of wildfires, as shown here, and low risk to help us really test our model in both scenarios. Our training process included 5 input layers with 1 output layer to train our model as to what an ideal result would look like. So our first one is the land fire mean return, which shows average fire return in an area, precipitation, which shows annual rainfall, our Sentinel-2, which is from the ESA's Sentinel-2 satellites to kind of show what land formations are in the area, land cover, which shows how humans are using the land, for example, vegetation, agriculture, and residential areas. Moisture deficit and surplus, which shows areas of high moisture and areas of high drought, which will be correlated with a wildfire risk. And lastly, our output, which is provided by the USDA Forest Service, shows once again what an ideal result would look like.
So now that we have our 5 input layers and our 1 output layer, the next step was annotating our data set. So we did that by drawing several different polygons for each type of wildfire risk, as you can see in the top left image. And this is essentially teaching our model how it needs to interpret the information and what to look for. For our model architecture, we actually implemented 3 separate models. The first of which was the UNet. The second is the DeepLab v3, and the third is a pyramid scene parsing network. The basic concept behind these machine learning networks is that you have an input image, which is converted from raw pixels into numbers. And then you have what's called a convolution, which is essentially a sliding window that goes over patches of pixels in your input imagery to extract the most important features. And that's all learned. And then finally, you have a neural network that's placed at the end of these convolutional layers to search through these different features and determine what's what in the final classification. So here are a couple of images of the different model architectures. The first is the UNet. It's a symmetric model with both an encoder and decoder side, along with skip connections to connect both sides and retain information. On the right is a picture of the DeepLab v3 model architecture. And the most important thing about this is that it has something called an spatial pyramid pooling module, which essentially, instead of just being one sliding window, it actually has several sliding windows at different fields of view, which gives the model a better idea of what it's looking at. And then the pyramid scene parsing network, likewise, instead of different fields of view, has different scales to again give the model a better context as to what to look for.
So these were our results. These results allowed us to analyze our performance over actual machine learning models. So our F1 score is a combined mean of both precision and recall. This measure indicates our model's performance across a single metric. And so as you can see, our UNet model performed the highest with 87.61%. As for recall and precision, recall indicates the proportion of true positives that were correctly identified by each machine learning model. Precision is the proportion of true positives that were predicted for each class, for example, high risk, low risk, medium risk, etc. UNet had the highest precision, while the pyramid scheme parsing network had the highest recall.
And these are our results graphs. So for each epoch, we actually calculated several different metrics, the first of which was accuracy. Final accuracy for the UNet was 80.9%. For the DeepLab v3, 76.7%, and PSPNet, 75.1%. And then additionally, we also calculated the validation loss. The final validation loss was 0.53 for UNet, 0.58 for the DeepLab v3, and 0.63 for the PSPNet.
Going into analysis and conclusion. Analysis based on our F1 and recall and precision scores, our models can realistically be deployed and used for various reasons by the general public and fire departments across California. Our next steps would be to increase our study area to include the rest of California and hopefully eventually the rest of the United States. How would we apply this model? Across the world, many communities don't have access to real-time wildfire risk maps that are both accurate, efficient, and accessible to them. As such, we would like to be the first in giving such an accurate model, and especially we want to help low-income communities that may experience several barriers that prevents them from understanding wildfire risk in their area and which prevents them from ultimately preparing for a wildfire event. Thank you. We want to thank all of our mentors that made this internship possible. We really could not have done this without you. We would like to thank all the organizations, the NASA SEAS program, UTA, Toledo, which you guys have been so amazing, and we're really thankful. Going into our personal reflections, both Hudson and I really loved working on this internship. It has been so nice to meet such great people, and we're really looking forward to taking this knowledge with us in the future. Thank you so much for listening.